In this video for AP Statistics, we are going to be talking about categorical data within sampling distributions. So, of course, if we're talking about categorical data, that means our data fits into one category or another. So, we are talking about the proportion out of a total that represents whatever category we're interested in. So, anytime we're talking about categorical data, we are going to base everything on proportions. So let's talk about the population parameter. Typically, this value is unknown. And why? So let's think about this. Let's say we're interested in the number of high school seniors who have a driver's license, okay, which of course it's going to be most of them, but not all of them. So if we're talking about the population being all high school seniors, let's say within the state of Texas, well, that's a lot of people. So it's not very realistic nor cost effective or time efficient to find all of that information for every single person in the population. So it's often that the population parameter is unknown, and we recognize that as P equaling X. In this case, it would be the number of high school seniors with a driver's license out of the capital N total population of Texas high school seniors. All right. So since we often don't know that, we often use a statistic from a sample that we feel is large enough based on certain conditions that are met in order to represent that whole population. And of course, when you're taking a sample, it's much more what's the word I'm looking for? It's just easier to manage, really. So P hat is going to equal X over little n representing a sample of a specific size that we feel is a good representation of the population. So when we're talking about estimating the population, we want to estimate that with a sample statistic. All right, and of course, when we sample, we are going to get sampling variability, which is perfectly acceptable and actually necessary in order to look at a distribution. So if you'll notice here, I've got written in repeated random sampling, the value of the statistic will vary. And let me show you what I'm talking about. If we look at this applet I have here from Rossman Chance, this is the Reese's Pieces applet, and we are told, it's common knowledge from the company, supposedly, that the probability of orange candies is 0.4. So I have that listed up here in this upper left-hand corner. And let's say I'm going to take a sample of 50 candies. Well, if I do that one time, then what it's going to do is it's going to sample 50 candies for me, it's going to count them, and it's going to show me how many of them are orange. In this case, 20. And then down here in the graph, it has plotted that value. Well, if I do it again, I am going to take another sample of 50. It is going to count out how many are orange again, and it is going to arrive this time at 29, and it is going to plot that on the x-axis. So I could do this all night because it's great fun, but in order to save some time, I'm going to go ahead and jump to 20 of these, okay? So I'm going to have it draw 20 more samples, and so now I'm getting a distribution of values. I've gotten that high one at 29, I've gotten a low one at 15, so I'm starting to get a distribution here. So let's do it again. This time, I'm going to go 50. I'm going to draw those samples. There we go. Now I'm up to 72. You'll notice it starts piling up there in the center. So now we're going to do this again. Now let's take 500. We're going to jump a lot. So now look what happens. I get a nice, beautiful, symmetric distribution. Pretty normal, right? And when I say normal, I mean normal as in symmetric, bell-shaped, unimodal. So this is kind of taking on a normal shape. So what does that mean? Well, it means that through sampling variability, I can see that all samples of 50 that would create a distribution of all of those samples, it's going to take on a normal shape. So 50 would be an acceptable amount to sample. So when we start looking at this, let's talk about the sampling distribution for my proportions and what samples are acceptable. We want to talk about conditions. Okay, so when we talk about conditions, they're all about the sample. And ultimately, what we want to do is we want to recognize that a sample meets certain criteria so that we can use the normal curve or the normal probability model to answer probability questions. So the first thing we need to pay attention to is this idea that randomization occurs. We want to make sure that our data comes from a simple random sample. That way we know that we're avoiding bias at all costs. We have to pay attention to the wording of the problem. Sometimes they'll tell you it's a simple random sample. Sometimes they'll say the data was randomly collected, etc., etc. So pay attention to that. The second thing is independence. Now, there's this idea that our sample needs to be independent from all of our samples, and each individual item within the sample needs to be independent. So in order to talk about both of those, we're going to break this condition into two parts, and we're not only going to say that the individuals sampled are independent of one another, we are also going to state that our sample is no more than 10% of our total population. So we also need to know that information. That's generally speaking a good place to be. So we want our sample size to be less than 10% of our total population. The other thing we need to address is this idea that it is large enough. If you notice from that example I just did with the applet, when you look at this distribution, I need to know if 50 is a good sample size. Well, if you'll notice, if I take lots and lots of samples of 50, it starts taking on a normal shape. This is a good indicator that 50 is a nice size sample for me. It's going to be big enough. So within each individual sample, what I want to see at least 10 successes and at least 10 failures. Think back to when we were talking about the binomial distribution. We had two possible outcomes. It was in this category or it was in this category over here. There were only two possible outcomes. So whatever my situation is, I'm going to have two possible categories, and I want to see at least 10 of each to know that I've gotten a sample that's big enough for using my normal distribution model. So for proportions, the way we discover that, we take the sample size times p, which is going to be our measure of center for our distribution, and to give you something to base that on, the probability of orange candies was 0.4. So that's the p that I'm talking about. So n times p has to be greater than or equal to 10. We want at least 10 successes. And n times 1 minus p greater than or equal to 10. Well, think about the orange candy situation. The probability it's orange is 0.4, so the probability it's not is 0.6. So this would represent orange candies. This would represent not orange candies. So we want to have 10 of each at least. And this idea that my sample's large enough is what allows me to approximate normal, because those larger samples tend to take on that normal shape when we're looking at a sampling distribution of lots of samples of that size. So that's the key right there. The size being large enough to approximate normal. That's the key. All right, so please keep in mind when we're talking about proportions, when we're looking for a standard deviation of a proportion, it's going to be this right here. And when we don't know the population, it's going to be this right here. It's just a change in notation. Sometimes you'll be given a problem and you'll know P, and sometimes you won't. Sometimes they'll tell you, here's p hat for this problem, or here's p for this problem. So when you're finding your distribution, remember that the mean of the p hat is going to be equal to p, whatever that is. It's usually given to you in the problem. Standard deviation of p hat is going to be p times 1 minus p over n. So depending on whether or not you have p hat or p hat will determine your notation there. Okay, so that pretty much clears up just a general information video about sampling distributions for proportions. We're also going to have a video on quantitative data.